Hey there YouTube, it's Jacob here, and today I'm going to be doing a sort of a teardown of a QSC PLX-3602 amplifier for you guys. I'm just going to show you the basic circuitry inside there and how some of it works, and just show you all the components and sections of the amplifier and kind of go a little deep into how they work, and just to kind of give you a little basic knowledge. And if you like to see electronics teardowns like myself, if you haven't already guessed, I'm an electronics geek. I particularly like power electronics engineering, and this happens to fall under that category of power electronics. There's some pretty beefy stuff inside here, so let's go ahead and take it apart and show you what's inside. Alright, here, so the first thing you may notice is that it's upside down. The amp is upside down. And the way these amps are built is upside down. The reason they build these amps upside down is so that if you ever spilt liquid, or if a foreign object, a conductive object or anything fell into the amplifier, or somehow made its way into the amplifier, it's the objective here is that it would fall onto the cover and not onto the surface of the board, which could short something out, or obviously cause a problem. So that's why they build these amplifiers upside down. It's sort of ingenious yet smart at the same time. So we're going to take a look at, just go over it real quick here. Coming in here, you have the power filters. You have the big filter inductors. They have both the hot and neutral on the same core. So one side's the hot, one side's the neutral. You have these big filter caps. Those probably help a tad with maybe power factor correction. It doesn't have really power factor correction built into it, but I'm sure they do help out just a little bit. But yeah, mainly for power filtering, to clean the power. But so coming in here, they have that. This is a strictly 120 volt model. It doesn't run 240. So what happens is it takes the 120 volts AC and it goes through a big bridge rectifier. Now the bridge rectifier is over here. That's the main one. I don't know if you can see it down there. So the AC lines come in there and it rectifies it to about, it's around 200 volts, 170 volts, because it, rectifies it and takes the peak of the AC, which peak of 120 volts AC coming from the wall is about 170 volts AC. So you have 6 200 volt capacitors. These are 2200 microfarads a piece. I don't know if we can check that out here. There they are. Oops. Come on, come on, come on, and bingo. 2200 microfarads, 200 working volts, 85 degrees Celsius capacitors. USA, holy crap, that's a first, huh? This amplifier is made in USA, shockingly. One thing that QSC can still stand on is they have, well, they're still a good brand. They're a really good brand, but they have their RMX series made in China, which is kind of, but they're a lower model anyways. But they have a lot of their stuff made in USA. They're still a good brand, but they're kind of falling behind because they don't make digital amps anymore. But yeah, Crown and a lot of other brands have been stepping into the digital amps, and people are going to those. But they make great analog amps. So there's, if you know, well, this is kind of hard to explain. There's a lot of these small capacitors here. There's a ton of small capacitors. There's two rails in here. There's a, like I said, about a 200 volt rail. Let's just call it a 200 volt rail. And there's a 90 volt rail, or about 80 volt rail. So the reason there's two different voltages is this is a Class H amplifier. Now a Class H amplifier is sort of like a Class AB amplifier, and if you don't know amplifier classes, you can look that up on Wikipedia. It's kind of interesting. It shows you how the amplifiers work. But there's two rails on here, and I'll show you here in a minute. Closer up, there's MOSFETs under here. There's a few MOSFETs, and basically what this amplifier does is it runs on the 90 volt rails when it's running lower power, and when it sucks a lot more power and it gets into a higher power, it actually has the MOSFETs which just switch over to the 200 volt rails. Actually, I think these capacitors are in series, and I think it puts out, actually, if I'm not mistaken, 400 volts. I'd have to test that, but I think these capacitors are in series. They look to be laid out in series, and it says up here 400 volts, so I'd imagine that this switch mode might put out somewhere around 400 volts. So that's these capacitors are in series, and that's a pretty high voltage rail there, but it's going to be plus 200 and minus 200 volts, and then you have a center tap on each one, and that'd be your ground, and then plus 200 and minus 200, so you could go plus or minus 200 volts on your speaker outputs. So I pulled the board out of the amplifier to show you a little bit better. There's, as I mentioned before, the AC capacitors coming in. There's 1, 2, 3, and there's 2 filter inductors. These two. Those just filter the AC coming in, and then it goes to the bridge rectifier right here. This is where all the power goes through, and it's rectified from the 120 coming in the wall. That goes, traced it back to these capacitors, so it is stored and filtered in these capacitors. From there, it goes to these IGBTs, or integrated gate bipolar transistors. If you look down here, they are GCE, gate collector and emitter. So those are IGBTs. And what these do is they are controlled by an IC. I don't know if it's one of these two guys here or one of these over here. I would imagine it's probably one of these guys. I'd have to take a look at what the part numbers on those, but anyway, it comes out of these switch it, and I'm going to actually hook these up to an oscilloscope here in a little bit and show you what that looks like. It's pretty interesting. And those come through here. They switch at a really high frequency, and they go into, they also pulse width modulate it as well. They pulse width modulate it and switch at a high frequency. Goes into this filter coil here and into the switch mode transformer. Coming out of the switch mode transformer, there's a lot of different voltage taps. A lot of different taps here. Let me see if I can turn around, get a little bit better light here. And it comes out of the transformer, and it's rectified through these rectifiers here. These are all 4 bridge rectifiers, and these are the output rectifiers of this transformer. High frequency and higher and lower voltage. Like I said, there's 90 volt rails and 400 volt rails, and these capacitors are in series. And then it goes to the power transistors and the MOSFETs down here. And I'm going to pull these heat sinks off to show you just what that looks like underneath. I'll pull one of them off because they are a little bit of a pain to do, and it's a little messy because there's thermal paste under there and whatnot. But yeah, I'll show you the output transistors and these MOSFETs that I was talking about to show you the dual voltage rails that the Class H amplifiers have. So I pulled off one of the heat sinks to show you the transistors underneath, and nothing that amazing. They're all upside down. The way they built this amplifier is actually really creative. Not like a lot of other amplifiers I've seen. Normally on a lot of other amplifiers I've seen the transistors are built up. In this case they're face down, and I like the way they built these amplifiers. It's really nice. They're a well-designed amplifier, but coming in here we just look at, and we see the big main power transistors, the BJT transistors. There's 4 of them. There's 2 channels on this amp, and each channel has 2 heat sinks. So under one heat sink you're going to have the NPN BJT transistors, the NPN, and under the other heat sink you're going to have the PNP. Now I'm not sure which is which. I'd have to let me see if I can crack one of these guys up here and just see the part number here. So under here we have the part number. I don't know if you probably can't see that on camera. It's going to be a C3263. So I'll put that in the description and you can check that out. Those are going to be your output transistors and main power. And these two guys here are going to be the little preamp transistors to these. So these are going to power the bases of these. Down here, if we look, there's a diode, but here's that that MOSFET I was talking about, and I don't know if we can. Ooh, that's sketchy popping that up. Feels like the legs are gonna break off of it. Man, I don't want to bend it too far. You probably can't see the part number on that, neither can I. So I got my flashlight here, and I can see, showing you that it's an international rectifier FET, and it's a IRF 1010E. So we'll look up a data sheet on that. I'll put that in the description here. And that's going to be the FET that switches between the dual voltage rails. So it'll switch between the high voltage and the 90 volt rails that I said. I don't even know if they're, I don't think they're 90 volt. The capacitors are rated at 90 volt, but the rails aren't quite 90 volts. So that's the Class H magic right there. What it does is, like I said, it switches between the two voltage rails depending on how much power you're drawing, and it keeps wasted heat because Class AB amplifiers generate quite a bit of heat, and they can waste a lot more heat if you have higher voltages going into them than what's needed. So what they do is they run a low voltage rail when you need low power, and when you all of a sudden when you draw more power, it automatically switches over to the higher voltage rail with this FET, and gives you the power you need exactly when you need it. It switches instantly. That makes the amp much more efficient, less heat wasted because of lower voltages, and just makes the amp run a lot more efficient when it's idling as well as when it's running lower power. So I got my flashlight here, and I can see, showing you that it's an international rectifier FET, and it's a IRF 1010E. So we'll look up a data sheet on that. I'll put that in the description here. And that's going to be the FET that switches between the dual voltage rails. So it'll switch between the high voltage and the 90 volt rails that I said. I don't even know if they're, I don't think they're 90 volt. The capacitors are rated at 90 volt, but the rails aren't quite 90 volts. So that's the Class H magic right there. What it does is, like I said, it switches between the two voltage rails depending on how much power you're drawing, and it keeps wasted heat because Class AB amplifiers generate quite a bit of heat, and they can waste a lot more heat if you have higher voltages going into them than what's needed. So what they do is they run a low voltage rail when you need low power, and when you all of a sudden when you draw more power, it automatically switches over to the higher voltage rail with this FET, and gives you the power you need exactly when you need it. It switches instantly. That makes the amp much more efficient, less heat wasted because of lower voltages, and just makes the amp run a lot more efficient when it's idling as well as when it's running lower power. So on the input section over here, like I said, I'm more of a power electronics guy, so I can tell you the basics of it. Not a hell of a lot of knowledge, not a hell of a lot of stuff over here, but you just got basic filtering in here. There's built in this amplifier, they have a built-in crossover, and it switches between less than 100 hertz or more than 100 hertz. So you're going to have a couple filter inductors. You can see some capacitors right here. So there's going to be capacitors to filter out the all the low frequencies and let 100 hertz and above through. And there's going to be inductors in there to let 100 hertz and below through. And then there's just a passive if you don't want to use the crossover, and that's just going to bypass all the filtering, or not all the filtering, but all the crossover filtering. There's still going to be some filtering in there. And then you have the outputs here. These are the output lines going to the speakers. You have a ground. You have two grounds. and you have a left channel and a right channel output here. And if you're using the bridge, it's just going to be these two channels out of phase here. So basically, when you bridge an amplifier, what you have is you have two channels. Normally you have two channels that are going with the cycle, positive and negative. They're switching really fast with the audio frequency, and they're relative to this ground line. So this line will go positive and negative relative to this ground line, and the same with this channel. And when you bridge it, you totally throw out these ground lines. You're not using the ground lines at all, and you're taking these two channels and you're putting them out of phase. So one channel will be doing plus 200 volts at peak power, and the other channel will be doing minus 200 volts at peak power. Versus if you're running a single channel, you can only go plus or minus 200 volts relative to the ground. That only allows you to push so much power through. When you bridge the amplifier, you're using both channels, and allows you to use both sides of the rail, plus and minus 200 volts at the same time, out of phase, giving you a 400 volt rail voltage output. And that's a lot of power, and that allows you to use both channels and push more power through it at the same time, and you're not using these center tapped grounds. So here we have the two channels out of phase with each other. So it's pretty simple. This is how bridge works. You have one channel doing plus 200 here. This is a plus, while at the same time you have the other channel taking care of minus 200. So this is the second channel, and this is the first channel. So the first channel is doing the positive, and the second channel is doing the negative, and between the two you have a really big peak here. And then as it goes to the other half of the cycle, now channel 2 is taking care of plus 200, and channel 1 is taking care of minus 100, or minus 200 volts, and you have a peak of 400 volts. That's twice as much voltage because you're using each channel 180 degrees out of phase. This channel 2 is going to always be the exact opposite of channel 1. They're always going to be doing the exact opposite, and one will be supplying the negative half of the cycle, the other channel will be supplying the other positive half of the cycle, and that's going to give you the full cycle, rather than one channel just giving its only 100 or 200 volts relative to 0 and minus 200 volts relative to 0. You're not really relative to 0 anymore, you're relative to the channel 2, which is minus 200, so between the two you have 400 volts. That gives you a lot more output power. So I just want to explain how this works real fast here. So on normally one or two channels, you can have the channels separate. So you have the 200 volt rails here. This channel has the 0, or the center tap of the transformer. That's the 0 rail, and it has plus 100 volts and minus 100 volts. Now these two rails relative to each other are 200 volts. Sort of like coming in your house, you have in the United States here 120 volts and 120 volts, and you have a neutral, and the two phases between each other are 240 volts. So 120 to neutral, 120 to neutral, 240 to each other, and that's how you can get 240 in your house. Same concept here. You have 0, a neutral, except it's not AC here. Well, it is AC on the output, but on the actual voltage rails it's DC, but an audio signal is AC. So it is AC. But you have a peak of 100 volts and a peak of a minus 100 volts per channel. So you have a 100 volt rail here and a minus 100 volt rail here, 200 volt rail altogether, because they're relative to each other, they're 200 volts. Same thing on the channel 2. So you have the same thing. And like I said, you have a set of NPNs and PNP transistors for each channel, and one set takes care of the positive, one takes care of the negative. Well, when you bridge it, almost started drawing the 0 there. There's not supposed to be a 0. There is no ground. You have channel 1 doing the positive and channel 2 doing the negative, or it may be the other way around. It's just one channel takes care of positive, one channel takes care of negative at any given time. So this channel 1, as I said earlier, has plus and minus 100 rail, and that's 200 volts, and this has 200 volts here. So you combine the whole thing, and it has 200 volts, and this has 200 volts. So one channel can give out its full 200 volts on the positive cycle, while the other channel can give a full minus 200 volts on the same cycle. So it's going to go plus 200, minus 200. You have a peak of 400 volts here between these two phases. So there is no it's not relative to this ground anymore. In fact, you could take this out. This is just to show you the wave. It's actually these two just channels here. There's not going to ever be a zero voltage line. It's going to go one channel and the other channel out of phase with each other, and that makes a lot higher peak voltages. In fact, if you took this channel, and I have done this before, and you feed the inputs to the channels out of phase, so if you have one channel going positive on a signal and you have the other channel completely 180 degrees out of phase, so let me draw that here first. So I have here an oscilloscope probe hooked up to the emitter of one of the input IGBTs. This goes to the input of the switch mode. This is switching the 120 volts rectified and filtered DC that's going to this transformer. It's doing the high frequency switching going to this transformer, and we're going to take a look at what that looks like on the oscilloscope. We'll go ahead and turn the amp on the screen here. Wait for the relay to kick, and there it is. Doesn't look like much, but if we zoom in, voila. So we're in 10 microseconds per division. What we have here is times 10 probe, so this is 50 volts per division, and it's peaking into the third division, so that's 150 volts per cycle, and then it's peak to peak 300 volts. And if we use the magical feature on this oscilloscope, we can go down, down one more, over, and this is a Tektronix 2230. Really cool feature here. And we go like this. Oh, we got to go into the storage mode. So we store that, and we will. It's already captured. So we use the cursors, and we're going to set one right there. We'll set the other right there. So it's about, it says 113 megahertz, 0.113. So it's about 100 kilohertz. I think this is a little off. I've gotten really detailed into it before, and I came down to the conclusion that it's about 100 kilohertz switch mode power supply. We can zoom a little bit more in on the cycles. It's pretty clean for what it is, and each IGBT, it's got two IGBTs doing that, and that's going to the input of the switch mode transformer. So this is the switch mode power supply frequency right here, about 100 kilohertz going into that switch mode power supply. So I just wanted to show you real quick how that bridge works. On the amplifier, I have both channels right now. We're playing a 1 kilohertz sine wave, and if I just tweak the volume knob, you can see here each channel is independent. We are in stereo mode right now, so each channel is putting out exactly identical waves. It's just that if I change the volume knob, obviously the intensity of the waves goes up and down. So let me just show you here. We just have each channel hooked up straight to the oscilloscope, and the grounds are connected through the chassis of the chassis and the amplifier of the chassis of the amplifier and the chassis of the oscilloscope are both grounded. So that's how we're connecting the grounds here, and this is each signal relative to that ground path. But what I want to show you here, this is where oh, there goes my signal generator on my iPhone. What I want to show you here is when you put these, when you put it into bridge, we go from these independent channels here. I'm going to go ahead and flip it into bridge to channels that are out of phase with each other. and that's where it changes. Now let me show you again. This here, if we had this cycle, it's relative to this ground here. That's not there right now because I don't have the ground. Like, this is the ground. So you can see that the let me center that there. The wave is relative. It's positive here, relative to this ground. And let's just call this, well, it's 1 volt per division. So let's just say this is 2 volts peak right here to this ground. So again, if I flip it into bridge here, and we have to freeze the image, well, now the 2 phases are out of phase. It's the same 2 channels, except this is channel 1 and this is channel 2, and they're playing the exact opposite. So now, instead of being relative to that ground line that was nothing, instead of being 2 volts, it's relative to this other channel. This is a whole 4 volt peak here, so you're getting twice the power output, and you're utilizing both channels to do that. So one channel's taking care of the positive half, and the other channel's taking care of the negative half. You add them together, and you get the bridged output. And the bridged output is twice as much voltage, and pushing twice as much power through the speaker ohm. And yeah, so the bridge just puts the channels out of phase with each other and adds them together to get twice as much power, and that's what it looks like on the oscilloscope. Well, that just about wraps it up for this video. I almost had a heart attack taking that damn board out of there, because this is a pretty expensive amplifier, and it was a little on the scary side taking that board out. It was a little bit of a pain how it's set in there, but I got it out, and that was scary for me. But yeah, that's about it for this video. If you have any more questions or anything you want to see on the board, or anything about that I didn't cover, on that you want to know how it operates or anything, I'd be more than happy to shoot you an email or possibly make another video in more detail about it. If you have any questions or comments about the video, just leave comments, send me an email, send me a little message on YouTube, whatever, and I hope you have fun.